Hey everyone, I'm Anish and welcome to PrepFusion. So today we'll be starting the lecture 3 of Routh Hurwitz Criterion, right? So before starting the lecture, like this lecture will be mainly questions, okay? But I had to stop the lecture in between the previous lecture, right? Because like we are going out of time, and like I gave you one question for the homework, so that question we'll solve and bit of theory we'll do, and then we'll start with our question solving session, right? So yeah. Like whenever you see questions, right, you pause that, then you solve it. So I have said this multiple times. Should I repeat it? Because you have to follow this, right? You have to follow this. So this was my like the previous question, and this was my second question, right? Second question. So what was this? So again, right, I had to again compute the Routh table for this one and check if the system is stable. Check if the system is stable or not. Okay. So if I compute, obviously it won't be stable because this is a ROZ example. So but still, let's check about the ROZ and how to calculate all those things, right? So ROZ does help, right, in few cases. When we will solve questions in the next question, right, we will understand how does my ROZ helps. So this is the second question basically. Okay, second question. So how does my ROZ help basically? So let's say I have like again like let's first compute the Routh table. So we'll compute the Routh table basically. So this will be s to the power 7, s to the power 6, s to the power 5, s to the power 4, s cube, s square, s, and s to the power 0. Okay, so yeah, this is basically my Routh table basically. Let me put this one up because I have less space, so I will reduce the size of this one. So if I reduce the size of this one, right, this becomes this. Okay, I have to further reduce the size. This can come over here, right? So this is here. So let me first write the first row and the second row, right? What will be the first row? First row is again 1, skip 1, 11, skip 1, 4, then 44. And what is this second row? It's 6, 6, and then 24 and 24. Okay, so these are the first row and second row. Now let's compute, right? So what is this? 6 times 11, 66, minus 6, that is 60, divided by 6. 60 by 6 is 10, right? So 10. Now 6 times 4 minus 24, that is 0, right? So 0. Now I have 6 times 44 minus 1 times 24. So what will this be equals to? And we have to divide by 6 also. So let me compute. Even without calculator also you can compute, right? How? 6 times 44 minus 24 minus 24 times 1 divide by 6. Now you don't compute, right? You just divide by 6. So if you divide by 6, this will be 44 minus 4, right? So this is 24 by 6, that is 4. So what I will get? I will get as 40. Okay, I will get as 40. So yeah, sometimes you don't have to use the calculator. Okay, only hand calculations will also work. So here I will get 40. Now here I will get 0, right? Why I will get 0? Because I have nothing here, right? And this will get multiplied with nothing, so this will be 0. Okay, you can also skip writing 0. Okay, nothing means 0 only. So now I am in the basically fourth row. So this is 10 times 6 minus 0 divided by 10. So obviously the shortcut, right? 6 will come over here. So 6 will come over here, right? The shortcut one. And now 10 times 24 minus 6 times 40, right? And divide by 10 itself. So again what I will do, just write 24 times 10 minus 6 times 40 divided by 10. Okay, so this is 24 minus 6 times 4. So this is 0. This is again 0, right? So I get 0. And what is this? This is this one itself, right? This one will come here. Okay, as there is 0. So I will get 24. This I just show to you just to explain you that yeah, I used a shortcut over here, right? So now what will this will be 0, 0, right? So 0 minus 0 divided by 6, so it is 0. So I think I will get a row of 0 over here, right? So this first element I get as 0. Now what is like this one? This is 6 times 40 minus 240. 240 minus 240 is again 0, right? So yeah, this is a row of 0 basically. So I will stop here. Okay, now what I will do, I will compute my auxiliary equation. Auxiliary equation will be this one, right? Auxiliary equation. Okay, so this will be my auxiliary equation basically. So this is my auxiliary equation. Then let me write a of s. A of s equals to basically 6s to the power 4 plus 24, right? 6s to the power 4 plus 24. Okay, so this is my auxiliary equation basically. Sorry, not plus 1, it is s square, right? S square, sorry, there's s square. Okay, this is my, okay, did I do, no, this is 24 only. So here the s square term coefficient is 0. I'm sorry. Okay, I'm sorry. So s square coefficient is 0, so this will be this one only. So this is my auxiliary equation. Now what will be my coefficients of this row of 0? I will just differentiate this one, right? So if I do the differentiation, dA of s by ds, I get 24s, right? So this is basically my coefficients of this equation, right? Oh sorry, this is s to the power 3. Okay, s to the power 3. So here I have 24 and this is 0 only. Okay, this is 0 only. So yeah, at what will be my roots? I can find my roots from here, right? So what will be my roots? So this is very interesting. I will come to the roots bit later. Let's first focus on my Routh array computation, right? So I'll come to the roots. Okay, so I got my auxiliary equation, so I'll copy this Routh table up until this ROZ. Okay, before this ROZ, obviously what you do is, like, you can't do it like me, right? I will just copy paste. No, you just write it inside also, like side beside this 0, right? You do that. Okay, so whatever suits you. Okay, so yeah, so my like coefficients will be 24 s cube, this is 0 s to the power 1 plus like this is plus 0 s to the power 1, right? So this is 24 and this is 0, and again this is also 0, so it doesn't matter, right? So now let's further compute this one. So what do I get further computing? That I get, this is again becoming 0, right? This is again becoming 0, but what is this becoming? This is now becoming 24, right? Here I have 0. Okay, shortcut will come, this will be 24. Okay, so this is becoming 0 and this is becoming 24. So again I have to use the case 1 of the special special cases for Routh arrays, right? So this will be assumed as epsilon. Okay, I will assume this one as epsilon. Now I will further continue my calculations. Okay, so if I continue my calculations, what will happen again, right? Here what will happen, this epsilon times 0 minus, this is 0 only, this is 24 times 24, that is minus 576 divided by epsilon itself, right? Epsilon. Now here I have 0, right? Here I have 0 and this is 24, so this will come over here, right? Shortcut. So this is 0 and this will come over here, so I will have 24 over here. I will have 24 over here, right? So right now this is 24. So now how many sign changes do I have? What was the condition for basically like the sign changes, right? They told us that above this one and below this one, how many sign changes I have. Okay, basically above the epsilon and the below the epsilon. Okay, so what do I see? Tell me how many sign changes there are. So if I look at this carefully, I have like one sign change here and one sign change here, right? So I have two sign changes, right? So how many number of roots I will have in the right half plane? I will have two roots in the right half plane, right? Two roots in the right half plane. So I will assume epsilon to be a small positive number. Okay, so you have to assume that basically. So epsilon is small positive number. This is plus, 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 this is also plus. I will assume epsilon to be a small positive number. Okay, that's how you basically calculate it. That's how you basically calculate. So this is plus and this is minus, I think, and this is plus. Okay, so what is happening basically? So how many? 1 2 3 4 5 6 7 8, yeah, 8 terms, yeah, correct. So I am getting one sign change over here and one sign change over here. So I have two sign changes, right? Two sign changes. So yeah, basically as I have number of sign changes, two, hence number of poles in the right half plane equals to 2. Okay, in the right half plane equals 2, right? Number of poles in the right half plane equals 2. So yeah, that is it basically. So now right now what's next? So the next thing is we got this, basically our system is not stable, that we know. Now let's come back to the roots. Let's prove that I have two poles at the right half plane. So you assume this as positive and then you follow along, right? That is the main procedure, like small positive number, okay, that you follow along. Okay, so yeah, even if you assume this is negative, right, then also your answer will be correct also, because if you assume this is negative, what will happen? Here I will have one sign change and here no sign change, then again one sign change. Whatever you want to do, you do. Okay, like if you assume this is negative, then what will happen? This will become positive again. Okay, so yeah, that is an issue. So what you do, you assume this as small positive number. Okay, so yeah, that you do. Now yeah, coming back to the root side. So coming back to the auxiliary equation, if I solve this one, 6s to the power 4 plus 24 equals to 0, then s to the power 4 equals to minus 24 basically, no, minus 4 basically, right? 6 is getting divided, minus 4. Now how can I compute this one? Computing this one is not that easy. Okay, so what I will do, simply, this is auxiliary equation, right? So I will get radially opposite roots, right? So I can write my minus 4 like this one. If you are able to follow along, I can write my minus 1 like 4 e raised to power minus j pi. Okay, I can write it like this one. If you understand this, well and good. So what is my e raised to power j theta? It is equals to cos theta plus j sin theta, right? So if you put this j equals to, sorry, not minus, plus pi, theta equals to pi, what do you get? If you put theta equals to pi, what do you get? Cos pi is minus 1 and this is j sin pi, which is 0. Okay, so that is exactly what I replaced my minus 1 with. Okay, now what I will do, obviously this is not for exam, right? Your exam portion is finished. This you have found out that my number of poles in the right half plane is 2. That's over, exam is over, right? Exam question is over. This is extra, okay, to like explain what is happening in the question. So now I have s equals to 4 e raised to power j pi, right? So what I can do, like this is s to the power 4, sorry. What I can do, I can take the s to the power of 1 by 4 on both sides. So I will take s to the power of 1 by 4 e raised to power j pi divided by 4, right? Okay, so this will give me only one root, but I have 4 roots. Okay, but this will only compute me one root. So why, how, I will not explain. Okay, this is not that information, this will only give me one root. So what I will get s equals to 4 1 to the power 4 e raised to power j pi by 4, right? So this is one of the roots. So what is 4 1 raised to power 4? It is basically equals to under root 2. Basically 2 square is 2 under root, you calculate, this is basically 2 square 1 by 4 e raised to power j pi by 4 equals to, this is 2 raised to power half e raised to power j pi by 4, right? So this is equals to s. Right? So yeah, this is basically equals to s. So now right now this is one of the roots. Okay, so what is one of the roots? So roots basically equals to 2 raised to power half into e raised to power j pi by 4. Now I can break this down, right? This is basically under root 2 into 1 by root 2, like cos pi by 2 plus j sin by pi by 2. So this is j by root 2, right? J by root 2. Okay, so now you multiply root 2, what do you get? You get 1 plus j. So this is one of my roots. Okay, now another one will be exactly radially opposite. So if I have a radially opposite root, so I will write here radially opposite root. Okay, so what I will write? I will write here is 1. This will be minus minus j. I hope like it's absolutely opposite, right? So this is lying somewhere in hand 1 plus j, and this will be absolutely opposite of the like radius, right? Absolutely opposite, symmetrical about the origin, right? So this will be here. Okay, not here, not here, this will be here. But what do you know? If we have complex poles, then we know we got 4 poles, right? Because this will have a conjugate and this will also have a conjugate. Why? Because my coefficients are real, like right, my polynomial coefficients are real. That's why I will get a conjugate. So this will be 1 minus j, and this will be minus 1 plus j. From here we can see I have 2 poles on the right hand side, right? Right hand plane. Okay, can I find the other 3 poles? So I have how many poles left? Yeah, I have other 3 poles left. Can I find my other 3 poles? Let's see. Okay, again what we'll do, use the long division method, right? So I got my 4 poles. Now I will write the factors, right? I will write the factors. So what is the factor? Factor is basically this one, right? Factor is this one. This s square plus 4 is the factor, right? If you multiply all of this 4, like how you multiply is this, like this one, right? So this is s plus j, s plus minus j, s minus 1 plus j, s minus 1 minus j. Okay, so if you multiply all of this 4, what do you get? You get s to the power 4 plus 4, right? You will get this one. Okay, you will get this one, trust me. Okay, you will get this one. So after multiplying all of this 4, you get this factor equals to 0 is a factor, right? Factor. So basically if I divide by the factor through the whole polynomial, then I will get my other factors. Okay, other factors. So yeah, let's get this. Let's get my polynomial. Basically, yeah, this is my polynomial, right? So to reduce the size, basically, else this will be very very hectic. So again I will use the long division method, right? This time I remember the names. Okay, I wrote the names, like here I wrote the names, right? Where is it? It's not here, not in this question. Previous, yeah, here, right? I wrote it like this is known as the quotient, this is known as the dividend, and this is known as the divisor. Okay, and this is the remainder basically. So this is the divisor which is dividing basically, and dividend is basically through which I am dividing. Okay, and quotient is the result, right? Okay, the amount that is the factor, right, that we have to multiply. Okay, that is the quotient, and remainder is how much is left. Okay, so yeah, so this is basically my dividend. Now I will write my divisor, which is s to the power 4 plus 4. Okay, change the color. And what is this? What is this? I will calculate this, right? Now what I will do, I will try to equate with the highest power. So this will be s cube. So this is s to the power 7 plus 4 s cube, right? Plus 4 s cube minus and this becomes 6s cube. Like this is gone, right? So this is 6x cube plus 11s to the power 5 plus 6s to the power 4 plus s cube plus okay, this is subtracted, right? This is subtracted, sorry, this is gone. 24s square plus 44s plus 24. Now what I do? Now I multiply by 6s square, right? 6s square. Now I multiply, so plus 6s square. So this is 6 s to the power 6. Now this is plus 24s square. So everything is getting cancelled, so I'm feeling happy. So I will be remained with this will be minus, this will be minus, so I will remain with 11 s to the power 5 plus 6 s to the power 4, and this is 44 s plus 24, right? So now again what I do, again I multiply by 11s, right? 11s. So if I multiply by 11s, what do I get? I get 11s to the power 5, and this will be plus 44s, right? So I will be remained with, I have to reduce the size just by a bit. So this will become this will be gone. Okay, this is minus, this is minus. I will be remained with 6 s to the power 4 and 24, and now we have to multiply by 6. Multiply by 6. Okay, so if I multiply by 6, what do I get? I get this is 6 s to the power 4 and 24 minus minus. So what do I get? 0, right? My remainder is 0 basically. Okay, remainder is 0. So my remainder is 0. Okay, so if my remainder is 0, this is my factor basically. So my factor is, so what I am trying to prove to you that these roots, right, will lie on the left half, right? As I have already found 2 right half poles, I won't have any more right half poles. That I already established with a Routh array. So here I will prove it to you by exactly locating the poles. So this is amazing that I am able to locate the poles of a 7th order polynomial. Okay, but obviously this has conditions, right? If I get ROZ, then it becomes very easier. It becomes very easy. Also, right, we can see that I don't have, like I will see also, I don't have any repeated poles, because how many number of ROZ I have? Only 1. So I have only one pole, right? That is not repeated. If I had 2 ROZ, I will have 2 repeated poles. Okay, so I hope that also clears a few things. So yeah, right, now what should I do is, this is the factor, right? So this is the factor. No, this is not the factor, this is the factor. So this is actually, okay, now finding the roots of this one is difficult. I won't like blame you. Okay, this is anyways not coming to exam, but this is a very famous equation. So here, right, first what you do, you test, right? Whenever you get a cubic, right, what you used to do in class 11th or 12th, what you used to do, you test with -1 or 2, -2, something like that, 1 -1 -2. So here if I put test, okay, s equals to -1. If I put s equals to -1, what do I get? I get -1 whole cube plus 6 into -1 whole square plus 11 into -1 plus 6 equals to 0. Okay, this is -1 plus 6, okay, -11 plus 6 equals to 0. Okay, so what do I get? I get 0. So this is satisfying, right? So hence this is satisfying. So my s equals to -1 is a root, right? So s equals to -1 is a root. So that is again very lucky, right? That is again very lucky. So basically now what we can do, we can simply like we got one root, so other 2 roots you can simply again do the long division, right? Long division method, like this one. Okay, I will just write here like this one, you do long division method. Okay, 6s square plus 11s plus 6, you again do that. What you will see is that you get other 2 root sets by long division by the other 2 roots are, okay, the other 2 roots are basically s equals to -2 and s equals to -3. Okay, so these are my other 2 roots. So how many total roots I have? S equals to -1, -2, -3. So these are all left hand side, right? None of them are at the right hand side. So hence I can see from here also that all of them are on the left hand side. So my left hand poles, number of left hand poles equals to how many? There I had 2 and here I have 3, so total 5. And number of right hand poles, sorry, there I had 3, sorry, there I had 2 and here, yeah, 3. Number of right hand poles, am I doing something? Yeah, number of right hand poles I have 2 only, right? Number of right hand poles equals to 2. So from here we can actually see where are the roots and where are the poles, right? So yeah, I hope you got the basic concept of this one. So this was actually very important to understand that like what happens actually in the roots. This is not for the exam, okay? This is not for the exam. This is just for the basically just for the intuition, right? Just understanding case, okay? So yeah, now we will go to the theory. Okay, let's now start with the theory. So before the question, right? Yeah, these are the few key points about my ROZ basically. Okay, so ROZ either represents marginal or unstable system. Okay, ROZ either represents marginal or unstable system. Okay, so basically, we already saw it. Right? If we have a ROZ, then obviously it will be unstable, right? Obviously it will be either unstable or marginally stable. Why? Either it will have imaginary roots, okay, or it will have like roots in the right half plane, okay, that may happen. So yeah, that is basically what my ROZ represent, and the auxiliary equation consists only of even powers of S because roots of the auxiliary equation will be symmetric about origin. Okay, as they will be symmetric, I must have two roots, okay, two roots. I can't have only one root, right? Like that you can think. Symmetric means I need two roots, right? That's why basically like this roots must be like the auxiliary equation must occur at the even power of s, then my row of 0 will occur at odd power of s, right? So these two are fixed. So if you get a row of 0 at even power of s, then you must have made any mistake. That this is what the mistake part, right? Now that's why you just check if your auxiliary equation must be on the even power of s and your row of z must be on the odd power of s, right? So yeah, now like there is no significance of last row of being row of z. If the last row is row of z, then it doesn't matter, okay? You assume that 0 as positive, right? That no sign changes has occurred, so you don't care about that. So if last row is coming roz, you ignore that, okay? You ignore that. If there are imaginary roots, the characteristics equation, then we will surely get a row of 0 in the Routh table, but converse is not, okay? So okay, sorry, this is actually written a bit wrong. If there are imaginary roots in the characteristic equation, obviously like in the equation, right, in the polynomial, if there are imaginary roots, then surely we will have a row of 0, okay? That is confirmed, right? We have a row of 0. But if we have a row of 0, then it may happen that the roots may not be imaginary as well. It may lie on the right half plane also, okay? So yeah, this is the converse thing. So if you have roots as imaginary, then you are 100% sure that you will get a row of 0. That is confirmed, right? You will get a row of 0. But if you're like, I'm talking about purely imaginary roots, right? Purely imaginary roots. So now, but the converse is not true, that if your roots aren't imaginary, then sorry, if you have a row of 0, then that may become like the root may come to be imaginary, or it may come to be symmetrical, right? Symmetrical. Converse is not true. So these are just theoretical point, not that important, but this was important, right? Just to check for your mistakes, if you have done any mistakes, right? So if more than one ROZ occurs, that represents the presence of repeated poles, okay? So basically if there are, as I mentioned, right, if there are more than one ROZ in the Routh array, then it means we have repeated poles. So I have also written previously, I will write it here again, that number of ROZ equals to number of repeated poles, okay? Number of repeated poles. Like I'm just baffling a bit because like I posted a status in WhatsApp and people are just replying like hell. Okay, I have to delete the status actually, that's why. Okay, I will delete it after like finishing this recording, okay? That's why that's why I'm just baffling a bit. Just increase the size of this one. So Okay, this is stuck actually. Oh, shit. Yeah, I can move it here. I can increase the size of this one. Okay, now this is connected with this one. Yeah, now it will connect. I have to size further increase. So this is basically the number of what the formula represents, right? Number of ROZ equals to number of repeated poles. Now we have a concept of internal and external product. So this is valid for only third order system, right? So we'll understand what does this concept mean. Okay, this is very useful to do your calculations quickly. Valid for only third order system. Okay, so now what is happening? Basically, for a third order system to be stable, right? For a third order system to be stable, for a third order system to be stable, what does it mean? This means that all my coefficients, this is the first condition, that the necessary condition, right? We already know this. All the coefficients of my characteristic equation must be positive or same sign and non-zero. So all the coefficients of characteristics equation must be non-zero or and sorry, not or, and of same sign and of same sign, right? So this is the first case basically. Now what is the second case? Second case is my internal product should be greater than my external product. Okay, now what does this internal product and external product mean? I will explain, right? So like IP represents internal product and my EP represents my external product. Okay, EP represents my external product. So yeah, now let's first do an example and from there we'll understand it. So basically this is a third order system and this is a generalized third order system, right? Now let me compute the Routh table for this one. So if I compute the Routh table for this one, what do I get? Basically I have a s cube, s square, s to the power 1, s to the power 0. Okay, now what else do I have? I have E0 over here and E2 over here, right? And I have A1 over here and A3 over here. Now if I compute the Routh table, what do I get? I get this one as A1 A2 minus, okay, this I need to make more space, A1 A2 minus A3 A0 divided by A1. Okay, and what is this term? The last row basically, this is 0 only, right? This is 0, so last row will be only this one, right? So here the first column of my Routh table must be positive, same sign. So like A0 A1, I know they are positive, right? I'm assuming they are positive, so this also must be greater than 0. So A1 A2 minus A3, and they should be non-zero also. Okay, greater than 0, basically that means non-zero. Okay, so this should be greater than 0. So A1 is non-zero, so I can simply multiply, and this is positive, this is positive also, so my inequality sign won't change, right? Inequality sign won't change. So A1 A2 minus A3 A0 is greater than 0. Now what is A1 A2? A1 A2 are the, we can say as internal products. These are inside the characteristics equation, and A0 A3 are the external, they are outside the characteristics equation, right? So this is known as the IP and this is known as the EP. Okay, from here we can derive that IP should be greater than EP, right? So this is how I got this relation. Now you might ask, why is this so useful? Why are you teaching us this? Because in few cases when you will get third order systems, right, and you have to check the stability, you can just do it like this in seconds, right, in seconds. Else you have to compute the route table. That will just waste your time. Okay, so that's why you should know the trick. Okay, so I have written down the condition. So now if this becomes 0, right, if this equals becomes 0, okay, this becomes a ROZ, this becomes a ROZ. Okay, now as above this one all of them are positive and below this one is also positive, what will happen? No sign change, right? No sign change. Then my roots will lie in the imaginary axis. Okay, then my roots will lie in the imaginary axis, and if my roots are lying in the imaginary axis and there is no sign change, none of the roots are in the right half plane, so one root will be lying in the negative left half plane of the S plane and two roots will be on the imaginary axis. Now for a third order system, if two roots are on the imaginary axis, what does that mean? That means my system is marginally stable. Okay, my system is marginally stable. That's why if internal product equals to external product, my system becomes marginally stable, and if internal product is greater than external product, I see my system is stable. And obviously the last case, if this is less than 0, okay, then what will happen? My system will become unstable. I will have poles in the right half plane. I will have poles in the right half plane of the geometric axis, right? So yeah, that is basically it for the theory part. Now let's go for solving the questions, right? So yeah, that is it for theory. Let's go for solving the questions. Yeah, sorry for the interruption. Actually, I had to reply to people in WhatsApp because they were just texting me constantly. So yeah, before like going into the questions, right, what I want to tell you is basically one thing that I told you about the sign change, right? In the previous question there I told you about the sign change. How you can assume is, if you don't want to assume this epsilon as positive, what you can do, you can look above this one and below this one. So above this one is positive, from positive I'm going to negative, right? From positive I'm going to something negative, because this is going to negative infinity. So this is negative, and then again this is positive. Like this also you can think that from plus to minus then plus. Okay, so we have two sign changes. Okay, so if you don't understand that method, that we're considering this as small positive number, because you have to assume it, right? If you consider this as a small positive number, this will come out to be something finite. Okay, else you can't simply put 0 over here. Okay, that is the issue, that is the main problem. That's why you assume this as a small positive finite value, then you check that what are my signs and how many sign changes do I have. Basically this is the plus, then minus, then again plus. So I have two sign changes. So first sign change and then again second sign change. So this is how my sign change occurs, right? So basically yeah, we did the roots also, so I hope you understand. Like I proved it to you also that my roots, two of them are coming on the left hand side, and basically other two are coming on the right, two of them are coming on the right hand side, and the remaining are coming on the either on the left hand side or the geometric axis. So these were my roots, right? Here three of them, like five of them were at the left hand side only, none of them were at the geometric axis, because I had real roots, negative real roots here. Where are they? Okay, yeah, negative real roots here. Okay, negative real roots, I have 5, so I should write this is looking like S, this should I write as 5. The color I should change here. And two right hand poles, right? So this will be basically this one. Okay, so yeah, so basically I hope you got to got the gist of the concept, right? This is a very like important question to understand. Okay, so yeah, those concepts are gone. Now gate questions, they come easy only, right? We will solve gate questions and you will see. So this is the first question. We have to compute the Routh table and find the condition for the system to be stable. Find the condition for the system to be stable if the OLT of the system is given below. So OLT has been given, we have to find the condition, we have to compute the Routh table and find the condition for the system to be stable. So what we can do, obviously we can find the CLT from OLT and then compare the characteristics equation. But there was one limitation of Routh table. What was it? We couldn't compute for e raised to power minus st. Okay, why? Because exponential function has infinite s terms, right? Infinite s power terms, that I already explained to you. So what we will do, we will take the linear approximation. So for computing Routh table, we will take the linear approximation of exponential function. This one will be here. Okay, so yeah, what will be the linear approximation? As I told, right, what was my e raised to power minus x can be written as 1 minus x. This is basically my linear approximation. So what I can do now is basically this will become 1 minus, okay, what was the basically my g of s? G of s was this one, right? E raised to power minus st by 2 divided by 1 plus not 1 plus, it was s into s plus 2, right? S into s plus 2. Okay, so this was my g of s. Now I can further simplify this one like this one, 1 minus st by 2 divided by s into s plus 2. Okay, so this is basically my OLTF. Now I will find my CLTF. So if nothing is said, right, nothing is said, I will obviously consider my unity feedback system. Okay, so obviously negative unity feedback system. So yeah, that what we'll consider. Let me take another page. So nothing is said considering negative unity feedback. Let me come to this side bit. Unity feedback. Okay, so yeah, we have to consider negative unity feedback. So basically what will be my CLTF? My CLTF will be g of s upon 1 plus g of s, right? So what will this equals to? So this will be simply equals to, I will have, like, I am directly writing the final result. Okay, and this will be s into s plus 2 plus 1 minus this. I should extend. So this will be 1 minus st by 2 and s square. Now I will like take the s terms together. So this will be s into 2 minus t by 2. Okay, then also take the constant terms together, right, clump them. So this will be 2. Oh no, this won't be 2. I have only one constant term, that is 1. Okay, so yeah, what is the condition for my CLTF to be stable, right? The characteristics equation should have negative roots, right? Obviously should have, I mean the real part should be negative, should lie on the left hand side of the S plane. So basically this is a second order polynomial. As it is a second order polynomial, I can write my characteristics equation. So I can simply, just by seeing the coefficient, I can tell which condition will satisfy my this system to be stable. So basically, right, all the coefficients must be positive, right? All the coefficients must be positive. It should be non-zero and not positive, non-zero and same sign. As this is positive, this has to be positive, right? Okay, so that's what we will do, right? That's what we will do. Basically, I will equate t minus 2 greater than 0. It can't be even equals to 0. If it is equals to 0, then what will happen? Tell me what will happen. Then the system will be marginally stable. Okay. So, like this is second order polynomial. You compute the Routh table and you will get your same exact relation, right? Condition basically. So my t still here, t should be t will go on that side basically. 2 will remain on this side, t by 2, and t should be less than 4. I will write this in different pen. No, I will write this in this color. T should be less than 4 basically. Okay, so this is my condition basically. This is my condition. Okay, this is the answer basically. So yeah, for the system to be stable, my capital T must be less than 4. Okay, stability. Basically what I will do, I will take this in the next page and write here also that all my coefficients should be positive. Else you compute the Routh table and you will see from there also coefficients should be of same sign. Okay, so yeah, this was it for this question. Now let's go to the next question. So what is the next question telling us? A system described by the transfer function is stable. So this system is stable, right? Okay, transfer function is given. This is not the OLTF, right? This is the CLTF basically. The constraints on alpha and k. So basically the question has told us that system is stable, so you have to find alpha and k such that the system is stable, right? So basically again the same thing, that find the condition for which the system is stable, telling the same thing. So if Routh question comes, it will be about stability and about this characteristic equation, but this we can use in some other chapters also. This Routh thing, right, we can use it some other chapters. We'll see, right? So yeah, now like let me get the conditions. So I will write the characteristic equation again. This is a third order, so again I can use that internal product and external product thing, right? So third order. So what is my characteristic equation? My characteristic equation is cube into alpha square plus Ks plus 0. Okay, is cube plus alpha square plus Ks plus 0. Okay, so this is basically my characteristics equation, right? So now what will the constraints? So if I use my method 1, right, method 1, what is my method 1? Method 1 is basically my internal product is greater than the external product. So my internal product should be greater than the external product, right? So basically what I can write in, what is the internal product is alpha times k. It should be greater than the external, which is 1 times 3. So alpha k should be greater than 3. So I got my answer instantly. Okay, so my answer is B, right? Answer is B. So now, right, if I if I want to compute this with Routh table, can I compute this? Obviously, like, to prove it to you, yeah, we can compute this with Routh table also. So let me take another page. Now let me write method 2 over here, and this will be Routh table. Okay, this will be Routh table, right? So if this is Routh table, so this is basically, I will start from s cube, s square, s1, s to the power 0, right? And what are the coefficients? 1 is 1, then I will skip this alpha, I will take k, and then I will skip this one. Then in the next row I have alpha and 3, right? 4 coefficients basically. So now, right, I will multiply this alpha times k minus 3. So by now you have been pro, right, at this Routh thing. So I hope so, at least I hope so. So this is 3 alpha minus k divided by okay, no, this is not 3, yeah, sorry, this is wrong. K alpha k minus 3 divided by alpha itself, and this is 0, right, because here I have 0. Okay, and again, right, this 3 will come over here, so this will be 3 and this 3 will be shortcut. So now basically this has to be greater than 0. Okay, for this to have no sign change, obviously alpha has to be greater than 0. So another condition is this coefficient has to be greater than 0. Also k individually has to be also greater than 0, right? Okay, so yeah, like that is also another case, that k has to be also greater than 0. So the condition, right, here I should write other conditions also, that alpha has to be greater than 0 and k has to be greater than 0. So these two conditions should also be satisfied because they should have same sign, right? And as this is plus 3 and this is plus 1, so these two should also be positive. That is also one condition. Okay, so here, right, this alpha needs to be positive and this needs to be positive. So if this needs to be positive, what does this mean? So from here I can understand that this needs to be positive, and here, right here, this alpha k minus 3 by alpha also needs to be positive. So alpha k greater than 3. Alpha k greater than 3. Okay, so yeah, this is cross verified that basically, yeah, I'm doing the same condition again. So this is the next question. You pause the video, right? You pause the video and check, like this is also gate question, and check how are you able to solve this or not. Okay, this is a very like simple question only, but just with a bit of twist. Okay, so let's see. What is this question telling us? This question is telling us a certain system has transfer function this. Okay, so transfer function it has told, but this is actually not the CLT, right? This is the open loop OLTF. Okay, so just be careful about that one. Okay, don't be like confused with the statement. Transfer function it is given. Okay, but this is the G of S is defined as the OLTF for the system. Okay, don't be confused. Now where alpha is a parameter, consider the standard negative unity feedback configurations as shown below. Okay, so we have been shown a negative unity feedback, and we have been given 4 statement. So now, right, this was for gate 2008. Now what may happen is, now MSQ has come, right? So they will put statements and there may be multiple select questions, so you have to select multiple options. Okay, so yeah, that is for the MSQ part basically. So yeah, now like what are the options telling us? Options are telling us the closed loop system is never stable for any value of alpha. Okay, if this was my transfer function, then this is true, right? Because this is positive sign and this is negative sign, so there is sign change, right, for second order in the coefficients. So this would have been true if this was my actual CLTF, but this is not my CLTF, this is OLTF, so this option is not true. For some positive values of alpha, the closed loop system is stable, but not for all. We have to check for this one. For all positive values of alpha, the closed loop system is stable. Again, we have to check. The closed loop system is stable for all values of alpha, both positive and negative. This may also be true. Let's see, but we'll check. Then we can say about this 3 statements. How? Simplify the CLTF, then compare the characteristic equation and compare its coefficients, whether they are positive or negative, or what are they. So what is my CLTF? CLTF is simply G of S upon 1 plus G of S. Okay, so CLTF is basically G of S upon 1 plus G of S. So CLTF is this one, then what is my G of S? G of S is this one, right? So this will be simply, I will directly write. Okay, I will not do the calculation. So this will become S plus 8 S square. So I have no, right, here I have 1 G of S upon 1 plus G of S. So the denominator will get multiplied over here, and my numerator will again remain here, right? So that's how I'm doing. So in exam also you should save time like this, right? Directly type. Obviously when you are totally like accustomed with this. So this becomes S square plus alpha S minus 4 S plus 8. Okay, so this becomes S plus 8 into S square plus alpha plus 1 minus 4 plus 8, that becomes plus 4. So now, right, I can see that this term has become positive and this is also positive, right? So at least these two can't, like, these are satisfying my condition for stability, right? Okay, let me write the characteristic equation. Characteristics equation is basically S square plus alpha plus 1 plus 4 equals to 0. So these two are positive, then this third term also needs to be positive. Okay, so again I will copy the previous statement only, right? This statement only. That all the coefficients must be of same sign, right? So if all the coefficients of same sign, then this alpha plus 1 also should be greater than 0. Okay, this alpha plus 1 also should be greater than 0. So if this is greater than 0, then alpha should be greater than minus 1. Okay, so alpha should be greater than minus 1, and this is the condition for stability. Condition for stability. Okay, so yeah, now but how can I say from here? So they are very gate is very good. Why? Because simply just giving alpha greater than minus 1 is of it's very simple. So they want to complicate a bit, so they gave you statements, so you have to read the statement and understand, right? So what is these three statement telling? So my alpha should be greater than minus 1, just remember that, right, for stability. So for some positive values of alpha, the closed loop system is stable, but not for all positive values. This is wrong, because alpha greater than 0 means all positive numbers. Alpha is even greater than minus 1, so alpha includes all the positive numbers, so this statement is not true. Then for all positive values of alpha, the closed loop system is stable. These two, right? Because alpha greater than 0 means for all positive values of alpha. That's what that statement means. So this option B is true, but still let's read the third statement. You should always read statements, right? For closed loop system, the closed loop system is stable for all values of alpha, both positive and negative. No, this is not true. Yes, it is stable for all positive values. It is stable for few negative values because alpha is greater than minus 1. That is the condition, but it does not include all the negative values, right? Obviously, it does not include alpha less than minus 1. All those all those are still on the number line, right? Less than minus 1. So it doesn't include alpha is only greater than minus 1. So it includes the whole positive thing, but it doesn't include the negative part. So my option C will be correct. Option C will be correct. Okay, so yeah, I hope you got this question. Now let's go to the next question. So what is this question telling us? Again, this is a gate question. Pause the video and try to solve it by yourself. So we have a feedback system, and we have been given a OLTF, right? And we have to find the condition at which the feedback system oscillates at 2 radian per second. So what does oscillations mean? So oscillations, right? Oscillations mean basically my system is marginally stable, right? Oscillations mean basically my system is marginally stable. So if they are marginally stable, then what does that represent? Okay, for a third order system, what does that represent? So I gave you some condition, right? Remember, about the internal product, external product, 3 conditions I wrote down. So just remember what happens for a marginally system stable. So my system is oscillating. When does that oscillate? For a second order system, remember, when does my system oscillate? It oscillates for undamped case. And in undamped, where does my roots lie? Roots lie on the j omega axis. What does that mean? That means my system is marginally stable. Here also my system will be marginally stable. Okay, now so let's solve this one, then we'll understand. So obviously this is the OLTF. We have to first find the CLTF, right? So method one is basically by checking the options. Okay, we will have multiple methods for this one. So method 1 is by simply checking the options. So I should come this side a bit first. So if I just check the options, what do I see? I see that first I have to find the CLTF, right? So let me first find the CLTF, then the methods will come, obviously. So this will be g of s upon 1 plus g of s. So this is k into s plus 1 upon s cube plus a square plus 2s plus k into s plus 1. Okay, so this is basically what my CLTF is. Now right now let me club the common test terms and the constant terms, right? So we club them, so this will be plus k plus 2 times s plus 1 plus k basically. Okay, so yeah, this is basically the characteristic equation. So okay, I will take this method to the next page. So my characteristics equation is this one. It is simply s cube plus a square plus k plus 2 into s plus 1 plus k equals to 0. Okay, so yeah, this is basically my characteristic equation. Now what is the condition? Basically my internal product, right, should be greater than the external product for y to be stable. But what was the other condition? If my internal product is equals to my external product, then what happens? Then the system becomes marginally stable, right? So what I can do, IP equals to EP, right? Then system is marginally stable. System is marginally stable if this is true. Okay, I should replace the color of this one. So now basically let me get the internal product. What is the internal product? It is a times k plus 2. So a times k plus 2 equals to, what is this external product? External product is 1 plus k into 1, right? So this will be 1 plus k itself. So what is my a equals to? A equals to 1 plus k by 2 plus k. Okay, so now I will just check the options. So gate also gave us options. So I think this question will not be solved in enough time, because if they don't give you options, right, it will be very difficult. So if they give you options, what will happen? Basically I will check for each option. So I'll check for first option, right? Okay, first option, what I will get? I will put k equals to 2 and a equals, I should get a should be equals to 0.75, right? So this is the first option. Okay, if I put this first option, what do I get? Like it's 1 plus 1 plus 2 divided by 2 plus 2, 3 by 4, which is equals to 0.75 itself. So my first option here is satisfying, right? First option here is satisfying. Now like obviously I should stop here, but as this question, as this calculation computation is very easy, right? Very easy. What I will do, I will still continue, right? So it must have happened I previously made some mistake. Okay, now as this computation is very easy, I will still continue and check all the options. If this computation wasn't easy, I would have moved on. Okay, I would have taken this one and moved on. But as this one is easy, I will still cross verify and check whether this step is correct or not. I may have made some silly mistake. Okay, so that's why you can check. If you have time, you can check. If you don't have time, you tick there and you go to the next question. So but I will check now. Okay, so if I check, okay, so option A is correct. That don't worry, option A is correct. Okay, but I should still check, right? So I will put k equals to 3 and I should get 0.75, which is not true. I put k equals 2 and I got 0.75, so this is not true anyway. So this is not true. Okay, because just by putting 2 I get the same, I can't get the same a, right, by putting different k. That is not possible. So now this is gone and I put k equals to 4, I should get 0.5. Let's see, if I put k equals to 4, what do I get? 4 plus 1, 5, 4 plus 2, 6. So 5 by 6 is not basically 0.5, right? It is something like 0.833, something like that, right? 0.833, something like that. So yeah, okay, is it correct? No, 5 by 6, 0.166. Yeah, I'm correct only. Yeah, 0.166 into 5. Yeah, 0.83 something. Okay, so it is not true. So C is also not correct. C is also C also not correct. Now what about my D? So D, right? D is k equals to 2 and a equals to 0.5. So if D is k equals to 2 and a equals to 0.5, again, right, if I put k equals to 2, what do I get? This is 1 plus 2, that is 3 divided by 4, that is 2 plus 0.75, right? So like I put k equals to, I should get 0.75, not 0.5. So again, this is wrong anyways, right? Wrong anyways. So yeah, that is how you can eliminate all the options. But the second method is basically Routh table. Okay, second method is Routh table, but you will get the same condition, and again you have to check options, right? So Routh table is the homework for you. I won't do, okay, because I should, few things you should do also, right? So that's how you will get the practice. So Routh table, okay, do the Routh table, then check the options. Obviously just one step more, check options, because if you try to equate both of them, right, there will you will get two equations. If you try to equate both of them, that will be difficult, right? Okay, so yeah, this was for this Routh table option. Now let's go to the method 3. Okay, this is a very interesting method, and you should always keep this in mind. This is a very good method. Okay, so what is the method 3? We have been given a very important information and we haven't even used it. What? This information, right? That my system oscillates at 2 radians per second. So if my system oscillates at 2 radians per second, what does that mean? When you used to say that my natural frequency is this, okay, my system is marginally stable and my system is undamped, and the roots were on the imaginary axis itself, conjugate imaginary, right? Roots are conjugate imaginary. That's when my system oscillates. So here also I have 2 radians per second, okay, and the roots will be conjugate imaginary. And those roots, what does roots mean? Roots means if I put the value of that equation on the characteristics equation, I should get my my equation should be satisfied. Basically, what is my characteristic equation? This one, right? This one is my characteristic equation. Now if I put the value of my roots in this equation should be satisfied, right? So that is what exactly I will do. Okay, so I will take the characteristic equation, and they have given us information, okay, that my system oscillates at 2 radians per second. Now what does this mean? This means that I know the location of two roots, okay, because it is oscillating. Obviously they will lie at the imaginary axis. Just think about the case of undamped, right? Undamped second order case, we already studied that, right? So they will be lying on the imaginary axis and conjugate form. So one will be here, and what will I write? I will write J2, right? J2, okay, J2, and this will be minus J2, okay. So yeah, so I know about the two roots. So if I put J2 here, this should satisfy the equation, okay, equals to 0. So that is what exactly I will do, okay. So I will put J2 here, J2, right? This is one of the roots. So what will this become? This is J2 whole cube plus a J2 whole square plus k plus 2 into J2 plus 1 plus k equals to 0, okay. So yeah, this is the equation. Now what I'll do, I will just simply equate the real and imaginary parts, right? So let me first tidy this one up. So what do I get? This one will be minus J8. I hope you know, right? I will write this one. So like J cube is minus J, right? J to the power, okay, I should write from starting itself. So J is under root minus 1. So what is J square? J square is, if I multiply minus 1 under root whole square, what do I get? I get minus 1 itself. Square root is there and I take whole square, right? So I will get minus 1. Now if I again multiply by J, okay, multiplying J on both sides, what do I get? Minus J, right? Minus J I will get. Now if I again multiply J, what do I get? Simply I will get plus 1, okay. You can think like this one also. I'm squaring this equation, right? So I will get plus 1. Sorry, this is not simple J, this is J to the power 4. So this is the circle, right? Circle of I, okay. So this is what? This is J plus J2 cube, right? So this will be minus J8. Now what do I do? This is J2 square, and we have A also. So A into J2 square, which is minus 4, okay. Now what is this? This is K plus 2 into J2. I will just keep this as it is. okay, plus k plus 2 into j2. Now what is this? This is 1 plus k, basically 1 plus k, right? 1 plus k. Okay, so yeah, now right, what I will do, this should satisfy, right? And what is the main thing, that my here it is equal to 0. So what does 0 represent? 0 means I can write this 0 in terms of imaginary and real component. So this will be 0 plus j0, right? So my imaginary component is 0 and my real component is also 0. So I will equate this with this one. So 11 in 11 12 we have done this a lot of times, right? When finding the square root of a complex number. So this, like, let me club the imaginary terms and the real terms together. So this is one of the real terms. So a and k are obviously real coefficients, right? This is real and this is real, and okay, this is not real. Okay, so my minus 4a plus 1 plus k. Okay, so I will write here that equating real and imaginary parts. Okay, minus 4a plus 1k equals to 0. So a is equals to simply 1 plus k by 4. This is one equation, and we have another equation. What is another equation? So another equation is minus this. I won't write j, okay, I will just write 8 because j is just the imaginary part, and the what is the like magnitude of the imaginary, that I will write. So minus 8 then plus, or you can write j also, it will simply get cancelled, right? Into 2 should be equals to 0. So basically k plus 2 should be equals to 4 and k should be equals to 2. Okay, from here I got the value of k, and I will put this here. I will get that my a should be equals to 0.75. okay, so this is also another elegant method of like solving this question, and this method, right, will be used in many other questions also. So just keep this in mind. If they have given you some information that my system oscillates, what does that mean? That means my system is firstly marginally stable. Okay, marginally stable system. Then I can know the location of the roots. Okay, I know the location of the roots. Okay, so yeah, this is a very good question. Okay, so we will actually end our lecture here because I had also a call coming up, and like this lecture has already gone over 1 hour. So we will end our lecture here and we'll restart our question session in the next lecture, right? So yeah, thank you for watching, and please do hit a like button if this cleared your concepts.